Sometimes science just doesn't play by the rules. You set up your models, gather your data, and expect everything to behave itself, except every once in a while it does. Numbers land way outside the range you'd bet on. Observations poke holes in theories people have spent years building. Basically, the universe likes to toss in something weird, something that refuses to fit into the neat categories and labels we trust. And then there are those quieter, stranger moments. Picture it, 3 in the morning, blue light from the computer screen. A scientist halfway through crunching numbers when something odd jumps out. They stop, lean in, try to make sense of a detail that doesn't belong there. Not because it's impossible, but because it lands right in that uneasy space, where what's normal ends and the unexplainable begins. 3IATLAS has become a magnet for moments like these. There's no wild headline-grabbing discovery, no obvious law of physics breaking in two. But there's this slow buildup, data point after data point, that just refuses to add up. Numbers strain the edges of what we know about comets, interstellar objects, all that space debris drifting between stars. Then came November 2025. Somewhere in the American Southwest, an amateur astronomer snapped a photo. Professional telescopes either couldn't match the clarity, or maybe they just let that detail slide in their official reports. The image, though, is striking. Instead of a fuzzy, chaotic smear, you see structure, clarity where you expect blur. It's not just a clump of rock and ice falling apart. It looks like it has edges, maybe even geometry, form. That single image, added to everything else we've seen from 3IATLAS, pushed a question into the open. A question most scientists would rather not ask, because it feels risky just saying it out loud. What if our models for these interstellar visitors are missing something? What if the tidy lines we draw, natural versus artificial, comet versus probe, geology versus technology, are just too simple for reality? Maybe the universe isn't interested in sticking to our categories. If you're as curious about this stuff as I am, hit subscribe and tap the like button. Your support helps these kinds of investigations reach more people who want real answers about the universe's strangest mysteries. Part 1. The structure question. The trouble started on a crystal-clear November night in 2025, one of those rare evenings in the desert when the sky feels steady and the stars barely flicker. The air was cold, dry, and perfectly still. Nights like this don't come often, and backyard astronomers dream about them. Paul Craigs had been waiting for his shot. He'd spent weeks tracking 3IATLAS, ever since the interstellar object brightened enough for amateurs like him to catch it. He already had dozens of photos, nothing shocking, just the usual, faint blur, soft glow, classic comet stuff. It matched what NASA and the ESA were saying. Just another comet, only this one came from beyond our solar system, dropping by before heading back into darkness. But tonight, something felt off. Craig set up in the patch of desert behind his house in southern New Mexico, a place so dark the Milky Way throws shadows. Out here, city lights can't touch the sky. His gear wasn't professional grade, but for an amateur it was pretty serious. A Dwarf 3 telescope, fully automated 150 aperture, sensitive CMOS camera. He'd spent years learning how to get the most out of it, stacking images, calibrating, processing, turning raw data into jaw-dropping shots that make the rounds online. He knew what his setup could and couldn't do. He could spot camera glitches, atmospheric blur, tracking mistakes, or the weird things that show up when you overprocess noisy data. He aimed at the coordinates for 3IATLAS, made sure the tracking was dead on, and kicked off the imaging run. The camera started snapping hundreds of short exposures, each catching a tiny flash from the distant object. Stacking software would then line everything up, blending out the noise and shaky air, pulling out details you'd never see from just one shot. That's how amateur astrophotography works. You tease the real picture out of the haze, find the faint signal hiding in all that noise, see deeper than your gear should really allow. The camera went for more than an hour. Craig sat inside, watching frames pop up on his laptop, the desert around him almost silent, just the odd coyote in the distance or a bat flitting past his porch light. He made coffee. He checked the weather, making sure clouds wouldn't sneak up on him. He scrolled through astronomy forums, reading what people said about 3IATLAS, the latest spectra from the pros, debates over what the thing was made of. Most of it was routine. Just another comet, they said, rich in carbon dioxide, odd in some ways but still fitting the comet mold. Nothing earth-shattering. When the sequence wrapped up, Craig's pulled the frames into PixInsight, the go-to software for serious astro imaging. He ran the usual calibration, subtracting out the darks and flats, cleaning up sensor quirks. He lined up the frames using star patterns, making sure every shot fit perfectly, even with tiny tracking errors. Then he stacked everything, merging hundreds of exposures into one sharp, quiet image. After that, he stretched the histogram, tweaking brightness and contrast to pull out the faintest details. This part always felt a little like art, a little like science. How much do you boost the signal? How much do you keep things honest? The final image depends on those choices. The image on his screen made him freeze. He leaned in, squinting, double-checking every step he'd taken. Had he messed up somewhere? This thing in front of him wasn't like anything he'd seen before. Not last night, not in the official shots from Hubble, not in any textbook comet. Comets are supposed to be fuzzy, wrapped in chaotic clouds of dust and vapor, smeared out by sunlight and space. But here, the core looked sharp, almost suspiciously perfect. Bright white, a little stretched, but the edges stayed crisp, even when he pushed his telescope to the limits. The stretch wasn't dramatic, maybe 50% longer than wide, but it was there, stubbornly consistent no matter how he looked at it. And then there was that blue glow. Not the messy, scattered kind you get from sunlight bouncing off ice, not the soft coma he'd cataloged 100 times. This blue formed a halo, tight and uniform, like it belonged there, like it was doing its own thing, not just tagging along with the dust. And honestly, it looked more like something shining than just reflecting light. He almost couldn't bring himself to admit it. Craig sat back, staring. He'd spent years chasing comets, and he knew their personalities. NEOWASC blazing its tail across the 2020 sky, Leonard in 2021, brilliant but always a little shapeless, its coma messy and restless. He'd seen the little ones too, barely more than smudges, but always with that classic soft-edged look. Comets are sloppy. They throw off material in fits and starts. As they spin, sunlight hits them in odd ways, launching jets that come and go. Sometimes they even break apart entirely, ripped up by heat or stray gravity. They're fragile piles of ice and rock, making a slow, inevitable mess as they fall apart under the sun. Nothing about them is neat. Nothing about them is precise. But this was different. This had structure, edges, a sense of order. Nature doesn't do order like this, at least not with comets. And the blue bothered him. Sure, sometimes you see blue in a coma from ionized gases, but never so pure. Usually it's mudded with yellow and red, the sunlight bouncing around with the dust. This blue was clean, almost artificial. It wrapped the white core neatly, like it belonged there, not leaking away into the void. He went back to his data, combing through every step. Maybe he'd overcooked the blue channel or tweaked the colors too far. He started from scratch, gentler edits, less noise reduction, every trick he knew. But that structure stuck around. Even the raw frames before any stacking or stretching showed it, faint but unmistakable. This wasn't just a glitch in the software. This was really out there, or at least as real as anything his camera could catch. He checked the stars around it, no weird shapes, no focus issues. His gear was working fine. Whatever this shape was, it came from the object itself. He saved the image and just sat there, watching the sky drift by outside his window. The stars kept turning, same as ever, totally unconcerned with his confusion. He knew what this image would stir up. People would say he'd pushed the data too far, or was seeing things that weren't there, or just didn't know what he was doing. But he'd done this for years. Galaxies, nebulae. Clusters, he'd squeezed detail from the faintest smudges of light, and knew how to tell real structure from wishful thinking. And what he saw in this shot of 3IATLAS wasn't what any comet was supposed to look like. Not even close. The next morning, running on just a few hours of shaky sleep, he uploaded the photo. He spent a while figuring out what to say, then posted it to Cloudy Nights, which is kind of the gold standard for amateur astronomers, a place where people really know their stuff and aren't shy about pointing out mistakes. His message was careful, almost sheepish. Imaged 3IATLAS last night under excellent seeing conditions, getting unusual clarity on the nucleus and some interesting structure in the coma. Possibly just processing artifacts, but wanted to share for feedback. Image details. Dwarf 3, 150 aperture, 500x10s exposure stacked. Standard calibration and processing workflow. Thoughts. He put everything out there. The full-raise image, his processing notes, even the raw calibration frame so anyone could double-check his work. He wasn't claiming a discovery or anything. He just wanted to know if anyone else saw what he did. The replies started pouring in right away, and wow, people had opinions. Within a few hours, dozens of comments stacked up. Some folks loved the image, saying he'd squeezed out incredible detail for an amateur setup, and that the seeing must have been off the charts good to get that kind of clarity. Others didn't buy it. They figured he'd pushed the processing too hard, maybe over-sharpened, maybe introduced weird artifacts with deconvolution. A couple of people pointed out that the Hubble images looked totally different, fuzzier, more diffuse. If billion-dollar space telescopes weren't seeing this structure, they said something in his process had to be off. But then things got interesting. Other observers started adding their own photos. An astronomer in Arizona, using a different telescope, a 200 Schmidt-Cassegrain with a different camera and software, posted an image from the same night. The structure showed up in his photo, too. It wasn't an exact match. The angles and processing were different, but you could see it. A sharp core, an elongated shape, a blue glow that seemed more organized than random. Then someone in Texas posted an image from 2 nights before, also with a different setup, and again, the same features popped up. At that point, it clearly wasn't just a fluke or a single overprocessed image. This thing was showing up across different gear, different skis, different nights. People's questions shifted from, "What did you do wrong?" to, "Okay, so what exactly are we looking at?" Professional astronomers started paying attention. Some messaged Craigs directly, asking for his raw data so they could run it through their own analysis. A researcher at the University of Arizona's Lunar and Planetary Lab wanted to use his image in a paper comparing amateur and professional observations of 3IATLAS. That kind of attention felt both thrilling and nerve-wracking. Craigs wasn't trying to stir up controversy. He wasn't claiming 3IATLAS was anything weird or artificial. He just posted what his telescope saw, what the photons from this visitor had left on his sensor. Still, you couldn't ignore the implications. If this structure was real, if it kept showing up for different people, then maybe the pros were missing something by sticking to certain processing routines, or maybe amateurs were just seeing details that didn't make it through the usual filters. The debate didn't stay on cloudy nights for long. It spilled over to Reddit's astronomy subs, to Twitter, to YouTube channels where people love arguing about cosmic mysteries. The mood bounced around from excited to downright skeptical. Some were convinced the images proved 3IATLAS wasn't a comet at all, that it was artificial, maybe even an interstellar probe. Others dismissed the whole thing, saying amateurs just didn't understand the pitfalls of image processing, and that this was all artifacts and wishful thinking. Then there were folks in the middle. Yeah, maybe the structure is real, but that doesn't mean it's anything unnatural. Interstellar comets take a beating from cosmic radiation. Their dust and surfaces could scatter light in weird ways. Basically, we shouldn't jump to conclusions after a few backyard telescope shots. Everyone had a point. Each argument came from a real, thoughtful place about how to handle tricky, ambiguous data. But honestly, underneath all the talk about processing methods and calibration and whatnot, a bigger, unspoken question sat there like a live wire, almost too risky to say out loud. What if the world of professional astronomy, with all its slow-moving institutions and love of safe, conservative answers, had built its own blind spots? What if all the rules, the standardized data pipelines, the endless peer review, the pressure to not make bold claims too soon, had started getting in the way? What if those same systems that are supposed to keep science honest and careful had begun to keep it from seeing something truly new? Big changes in science don't usually come from sticking to the plan. Again and again, The breakthroughs have arrived from outsiders or from oddball data that just wouldn't fit the old models. Galileo's discovery of Jupiter's moons upended everything people thought about the cosmos. Two engineers, just tinkering with satellite equipment, stumbled onto the cosmic microwave background and ended up confirming the Big Bang. Pulsars. At first, astronomers thought those were just glitches. Turned out they were looking at a whole new kind of star. Science moves forward by slow, careful steps, sure, but also by those moments when someone stares at a weird bit of data and says, "Wait, what if we're wrong? What if the universe is even stranger than we imagine?" 3IATLAS was one of those moments. Not a thunderclap, not definitive proof, but it was there, quietly piling up odd observations, a structure where there should have been a blur, measurements that stretched the old models to their breaking point. The standard explanations didn't quite cover it, and you know who really pushed this forward? Not the big institutions, but the amateurs. They weren't stuck following someone else's rules. They processed their own data, tried new things, and ended up putting the strange stuff right in front of everyone. Suddenly, you couldn't just ignore it or sweep it away with the usual methods that are supposed to make everything neat and predictable. Craig's image became the center of the debate. It spread everywhere: articles, forums, anywhere people cared about 3IATLAS. People argued, reprocessed, tried to confirm or shoot down what it showed. And really, no matter how it eventually gets explained, whether the structure turns out to be real or just a trick of the eye, the image already did something important. It proved that how you look matters. The choices we make about which tools to use, which assumptions to bake into our software, even how we expect things to look, all of that changes what we notice and what we miss. Maybe, just maybe, we got too confident about understanding interstellar objects. Maybe we tried to draw conclusions too soon, with too little data and methods too bound up in what we thought we should find. The question about the structure is still out there, and it's not going away anytime soon. Craig isn't some beginner. He spent years photographing comets, asteroids, deep space. He knows what fake structure from processing looks like. He's seen how stacking images can mess things up, how compression makes edges that don't exist, how too much exposure can turn a faint patch into a bright, fake-looking blob. So he went over his data, checked for mistakes, reprocessed with different settings. The structure still showed up. When he finally posted the image, adding a careful note about the odd clarity, the reaction was instant and completely split down the middle. Some people just wouldn't buy it. They were convinced the images must be overprocessed. No way, they said, could backyard gear show details that Hubble or other top-tier telescopes had missed or blurred out. But then others jumped in to say Craig's wasn't the only one seeing this. Within days, more amateur astronomers, using similar setups, shared their own images. Sure, they weren't identical. Everyone uses different equipment and catches the object at different angles. Still, the same main thing kept showing up. Way more detail and structure than any comet model predicted. Pretty soon, forums all over the place, amateur astronomy, planetary science, those obsessed with tracking interstellar visitors, lit up with arguments. Some threads got technical, diving into image processing and optical artifacts. Underneath all that, though, a bigger question kept bubbling up. If a bunch of independent observers are all seeing structure, is it actually there? The professionals, to their credit, didn't just jump on board. They showed the right amount of skepticism. When a backyard telescope image claims 3IATLAS looks totally different from what's in the official records, you have to take a hard look. Calibration is the go-to explanation. Amateur telescopes just don't have the strict calibration routines of pro setups. They're more likely to pick up errors, get thrown off by local weather or city lights, or introduce weird artifacts during editing. But that only goes so far. When people using different gear in different places keep picking up the same thing, it gets tough to say it's just a mistake. Either everyone's making the same error, or they're seeing something real that professional instruments are somehow filtering out. This gap between what amateurs and pros see isn't new in astronomy. It's happened before. Sometimes amateurs, who aren't weighed down by institutional assumptions or strict processing habits, spot things that the professionals overlook. Supernovae, variable stars, surprise comet outbursts. Amateurs have caught them first, just by looking at things from a fresh angle. So, is 3IATLAS another one of those moments? Or does this difference hint at something a little more unsettling? Now, you have to be careful with the word structure. In science, it means something specific. Order, patterns, anything that isn't just random noise. Plenty of natural things have structure. Crystals, planetary rings, even clouds of gas if you look close enough. But the structure in Craig's image and in the ones that followed feels different. It's too sharp, too symmetrical, and it keeps showing up no matter where or how it's observed. Comets break up, spin, change as sunlight hits them unevenly, and their glow, what's called the coma, should shift and blur over time. But these November images, they're weirdly consistent. The core doesn't seem to change, and the surrounding light looks like it's following rules, not just drifting off into space. NASA hasn't budged from its official line on 3IATLAS. According to them, it's an interstellar comet. They point to its path through the solar system, the light it gives off, and how it behaves. Nothing turns up as artificial. No strange radio signals, no oddball materials, nothing you couldn't explain with normal comet science. The European Space Agency says pretty much the same thing. Top researchers keep telling reporters, just because it's weird doesn't mean it's alien. Interstellar objects naturally look and act differently. They grew up in other star systems, after all. All of that makes sense. It's solid science. But still, those images are out there. People, pros and amateurs alike, keep looking at them, arguing over them, and they just won't go away. This isn't a fight between science and pseudoscience. It's more like a tug-of-war between two ways of looking at the same pile of data. One side says 3IATLAS is a comet. An oddball, sure, but a comet all the same. Just weird because it came here from another star and spent eons getting blasted by cosmic radiation. The other side looks at those grainy amateur images and wonders if there's something more going on. Something that doesn't fit the usual comet playbook, something that might force us to rethink what's actually out there drifting between the stars. Nobody shouting aliens. Nobody spinning conspiracy theories. Both camps are just looking at what's in front of them. The real disagreement, it's about how much to trust the odd stuff in the data and when it's time to start questioning the basics. On December 7, 2025, a group from the University of Arizona shared some early results from their close-up look at 3IATLAS using the Large Binocular Telescope. Their paper, still waiting on peer review, mostly dug into what the object reflected and what its fuzzy coma was made of. But hidden deep in the technical jargon was a short note. They'd found unexpected spatial coherence in the dust around the nucleus. In plain English, the dust wasn't spreading out the way comet dust usually does. Instead, it was sticking together in a way their models didn't predict. They didn't make a big deal out of it, just a cautious note, more questions than answers. But there it was, real structure picked up by professional instruments. After that, nothing. No big press release. NASA kept quiet. The preprint stirred up some talk in specialist corners, but it never hit the big science news sites. That's how science rolls when the data is weird but not quite enough to call it a breakthrough. Researchers hang back. They collect more data, tweak their models. They avoid going out on a limb because if they're wrong, that limb snaps and careers take a hit. But while everyone waits, silence takes over, and in that quiet, questions start to pile up. Why isn't anyone talking? What's going on behind the scenes? Is caution turning into a kind of censorship, keeping the public in the dark? These aren't wild conspiracy theories. They're just the questions anyone would ask. When something looks strange and the official story feels thin, it's only natural to get curious. The trick is holding onto that curiosity without running off into fantasy, asking tough questions without jumping straight to cover-ups, respecting the careful pace of science while recognizing it doesn't always give us answers when we want them. 3IATLAS is forcing us to get comfortable with not knowing, to sit with uncertainty longer than we'd like, and to keep our cool while the story unfolds. And here's the thing that makes all of this feel urgent. 3IATLAS isn't waiting around. It's moving, right now, through the solar system, and in a few months, it'll whip past Earth and disappear into interstellar space. The chance to figure out what it really is won't last. If we're going to get answers, we need them soon before it slips away for good and becomes just another mystery in the cosmic catalog. Time's running out. The data is piling up. But that weird structure, whatever it means, still hangs in the air, unresolved, daring us to solve it before the window closes. Some people immediately dismiss the amateur images, insisting they were just overprocessed, that backyard gear couldn't possibly pick up details the Hubble missed. But others noticed something. Craig's wasn't the only one. Within days, other amateurs, using similar setups, snapped images that showed the same thing. Not identical, of course. The equipment and angles varied, but the key detail held up. The object had much more structure and clarity than standard comet models allow for. The debate exploded across forums, from amateur astronomy to planetary science, and among everyone obsessed with these visitors from other worlds. And underneath all the arguments about image noise and artifacts, a bigger question started to bubble up. If independent observers keep seeing this structure, maybe it's not a trick, maybe it's real. Astronomers didn't just accept the new images, they questioned them as they should. Big claims need close inspection, and let's be honest, a backyard telescope showing 3IATLAS looking totally different from official photos is a big claim. Most professionals chalked it up to calibration. Amateur gear just isn't built like the stuff in observatories. It's more likely to pick up errors, more sensitive to local things like humidity, light pollution, or even mistakes in photo editing. Still, that only explains so much. When people in different places, using different telescopes, all spot the same weird patterns, calling it a fluke starts to sound flimsy. Either everyone's messing up the same way, or there's something real there, something the pros are missing or filtering out. This kind of split isn't new in astronomy. There are plenty of times when amateurs, not tied down by the routines or assumptions of big institutions, notice things first. Supernovas, variable stars, sudden outbursts from comets. Sometimes it's the backyard astronomer who catches them, simply because they see things differently or process data in their own way. Maybe that's what's happening with 3IATLAS, or maybe this time the disagreement is hinting at something stranger. Now the word structured can get tricky. In science, structure means there's some kind of order or pattern, something that's not random. Nature does this all the time. Crystals, the rings around planets, even messy gas clouds can show structure if you look at the right scale. But what shows up in Craig's photo and others like it doesn't fit neatly into those categories. It's almost too perfect, symmetrical, persistent no matter how you look at it. Real comets break up, spin, react to sunlight, shift, and blur over time. You'd expect the glowing cloud around 3IATLAS to change shape, but in these images it just doesn't. The core stays stable, the glow looks organized, not chaotic. NASA keeps its language careful and steady. They call 3IATLAS an interstellar comet. That, based on how it moves, its chemical makeup, and what it's doing out there. No sign of anything artificial, no weird radio signals, no strange materials, nothing you couldn't explain with what we know about comets. The European Space Agency agrees. Top scientists interviewed by reporters keep repeating it. Just because something's weird doesn't mean it's unnatural. Interstellar objects can look odd because they're formed in other places under different conditions. It all makes sense. It's all logical. Even so, the images keep showing up. People keep talking about them, both professionals and amateurs, and no one seems able to just shrug them off. It's not really a fight between science and nonsense. It's about how you look at the same data and see different things. One view says 3IATLAS is just an unusual comet, strange looking because it's from another star system, shaped by cosmic radiation over millions of years. The other view looks at those patterns in the amateur photos and wonders if we're seeing something new, something that doesn't fit neatly into the comet box at all. Nobody shouting about aliens or cover-ups. Both sides just want to get it right. The real question is, how much do these odd details matter? And at what point do you start rethinking what you thought you knew? On December 7, 2025, A group of astronomers at the University of Arizona put out some early results from high-ray spectroscopic scans of 3IATLAS, all done with the Large Binocular Telescope. Their paper, still a preprint, not yet peer-reviewed, dug into the object's surface reflectance and the makeup of its coma. But tucked away in the technical details was a quick note about something weird. The dust right near the nucleus was showing unexpected spatial coherence. Basically, at wavelengths where comet dust usually looks messy and scattered, they saw structure, real organized structure, picked up by professional gear. The team sounded careful about it, almost wary, saying more work was needed, but they did admit the dust around 3IATLAS wasn't acting like the models said it should. Then nothing, just silence. No splashy NASA statements, no media buzz, not even a ripple outside of some niche astronomy forums. Science is often like this. When the data pokes holes in what people expect but doesn't quite settle anything, the experts go quiet. They wait, gather more data, tweak their models. Nobody wants to jump the gun and risk looking foolish if it turns out to be a fluke. But all that waiting leaves a gap, and in that gap, the questions pile up. Why the hush? What are they seeing that they're not ready to talk about? Is all this caution just the system working, or is it holding back something the public should know? These aren't wild-eyed conspiracy questions. They're normal. When something doesn't add up and the official story feels thin, it's natural to get curious. The trick is to stay curious without sliding into wild guesses, to push for answers but not assume there's a cover-up, to respect the slow grind of science while also noticing its blind spots. 3IATLAS is putting us right in the middle of that tension. It's forcing us to sit with not knowing, to practice patience when the evidence just won't snap into focus. And here's the thing, this isn't a problem we can let simmer forever. 3IATLAS is on the move, streaking through the solar system. In a few months, it'll swing past Earth and then vanish into interstellar space. The window for new observations is closing fast. If we're going to get answers, we need them soon, before this object slips away and turns into another question mark in humanity's long list of cosmic mysteries. Time's running out. The data is stacking up, and that weird, unexpected structure, still hanging there, unresolved, daring us to make sense of it before 3IATLAS disappears for good. Part 2. How discovery was supposed to work. To get why 3IATLAS stands out, you have to know how astronomers usually spot and track interstellar objects. It's a pretty tight process, built up over decades, and it's all about catching anything zipping through the sky that shouldn't be there. It starts with these automated survey telescopes, huge cameras that scan the sky every night, snapping images and sending them straight into software designed to look for movement. The software's job is simple. Pick out the moving blips from the endless static of stars and galaxies. Most of what pops up isn't a mystery. It's the usual suspects: main belt asteroids, well-tracked near-Earth objects, satellites, and leftover junk from old rockets. The system cross-checks all of this and throws out anything familiar, leaving only the weird stuff, objects in strange places, moving in odd directions, at speeds that don't make sense. ATLAS, short for Asteroid Terrestrial Impact Last Alert System, runs 2 telescopes out in Hawaii with NASA footing the bill. They're built for exactly this purpose, to spot dangerous asteroids before they get too close to Earth. Each telescope sweeps a huge patch of sky, taking multiple shots a night to catch anything moving. On July 1, 2025, ATLAS picked up something odd, a faint smudge drifting across the stars. At first, it looked like a comet, maybe one of those long-haul visitors from the Oort cloud, that icy graveyard way out at the edge of the solar system where comets hang around for ages until something nudges them sunward. But when astronomers ran the numbers, the object was moving way too fast. Its path wasn't just a stretched-out oval, it was hyperbolic, meaning it wasn't tied to the sun at all. This thing wasn't just another solar system comet making a rare visit. It was from somewhere else entirely. Just the third time we've ever seen an interstellar object, after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The discovery set off a chain reaction. Everyone knew the drill. Telescopes all over the world, Big professional setups from the US to Europe to Chile and Australia, plus dedicated amateurs, swung around to the coordinates from Atlas. The International Astronomical Union stepped in and gave it the official name, 3IATLAS, marking it as the third of its kind and crediting the team that found it. NASA's Planetary Defense Network started tracking the newcomer, using radar and infrared to nail down its orbit and check if it posed any risk. It didn't, thanks to its hyperbolic escape route. Even the Hubble and James Webb Space Telescopes, the crown jewels of astronomy, squeezed in time to study it. This is just how things work now. A global, coordinated response, practiced and polished, ready to jump into action whenever something from another star system drops by. At first, everything about 3IATLAS looked familiar. The early data matched what astronomers expected, right in line with models built from decades of watching comets in our own solar system. Using spectroscopy, basically splitting up the light to see which molecules are there, researchers spotted water vapor, carbon dioxide, and carbon monoxide. All the usual suspects, all the signs you expect when a comet's ices start to vaporize as it gets closer to the sun. Images showed a coma too, that ghostly cloud of gas and dust around the nucleus. That's a classic giveaway. The comet was shedding material. And as it swung closer to the sun, a faint tail formed, streaming away just like it should, pushed by sunlight and the solar wind. By every test, by every measure, 3IATLAS acted like a comet. Sure, it was from another star system. That was wild. But in terms of behavior and activity, it fit the playbook written by comets from our own backyard. The first scientific papers told the same story. The language was technical, full of error bars and confidence intervals, careful about what could actually be claimed, but the bottom line was clear. Here was an interstellar comet, heavy on carbon dioxide compared to water, which is a twist, since most local comets carry more water ice. It behaved like any other comet. It heated up as it neared the sun, started outgassing, and the rates matched what you'd expect from a nucleus a few kilometers wide. The papers went through peer review, where other scientists checked the numbers and poked at the conclusions, making sure everything held up. In the end, the journals published them. 3IATLAS slid smoothly into the official record, and the big machine of scientific discovery rolled on. Then October 30, 2025 hit. That's when 3IATLAS reached perihelion, its closest pass to the sun, about 1.4 astronomical units out, just inside Mars's orbit. 1 astronomical unit is the distance from Earth to the sun, about 93 million miles or 150 million kilometers. This is when comets really show off. Solar heating is at its peak. The nucleus gets hot, ices sublimate like crazy, jets of gas burst out, dust lifts off the surface. And the tails get long and bright. Observers saw exactly what the models predicted. The comet got brighter, the coma swelled up, everything looked textbook. But then the story took a turn. High-resolution images started coming in from ground-based observatories with adaptive optics, those fancy systems that use bendable mirrors to cancel out the blur from Earth's atmosphere. These telescopes can see nearly as sharply as space telescopes, even from the ground. And what they saw didn't quite line up with expectations. The nucleus looked more compact and denser than the size estimates suggested, not the loose, fluffy clump of ice and rock people expected. The coma, while active, had less debris than it should have for the amount of material the comet was shedding. Maybe the comet was giving off more gas than dust, or the dust itself was unusually fine and dark, not reflecting much light. Even stranger, the way the light scattered. The polarization was off. Specialized instruments measured light bouncing off the dust and ice, and the results didn't match any comet on record. The particles seemed oddly shaped, or maybe made of something with strange optical properties. It was still a comet, but now it was clear. This one was different. None of these observations on their own proved anything extraordinary. Science isn't about absolutes. It's about ranges, odds, and patterns. Outliers pop up. Weird mixes of properties happen. Sometimes something looks unusual, but it still fits within the rules of physics. We don't need to rewrite the textbooks every time something odd shows up. Most of the time, when you dig deeper, get better data, sharpen the analysis, or realize the first measurements were shakier than you thought, those anomalies sort themselves out. But when the oddities start piling up, when different teams using different tools all agree something's not quite right, the question changes. It stops being, "Is this normal?" and turns into, "Why isn't this behaving the way we expect?" That's a small shift in phrasing, but it means a lot. Suddenly, it's not just about sorting something into a familiar category. Now you're forced to explain it. You start to wonder if our models really cover everything, or if there's more out there than we thought. People at NASA's Jet Propulsion Lab in Pasadena, where they handle solar system dynamics and planetary defense, and at the European Space Agency's Near-Earth Object Office in Italy, handled these weird findings the way you'd expect from experienced scientists. Carefully, cautiously. That's how they've been trained. Press releases kept calling 3IATLAS a comet. They used the usual language, focusing on how it matched what we already knew, not how it stood out. They explained that interstellar objects naturally look different from local ones. They form around stars with different stuff in them, in disks with all sorts of odd ingredients. That wasn't spin or some cover-up. It's just how responsible science communication works. You don't freak people out with early data that might fall apart later. You wait for confirmation, for other teams to check your work, for the whole process to play out. You give the public your best understanding based on what's solid, and you're upfront about what's still uncertain or speculative. Still, caution, no matter how reasonable, gets misunderstood, especially by people following the story from the outside, through independent sources or amateur observations that paint a different picture than the one in official channels. Social media and forums run wild with speculation, way faster than peer review can keep up. To these folks, especially those comparing crisp amateur telescope shots with the fuzzy, washed-out images from Hubble or other big observatories, the careful language in official statements started to sound like dodging the issue. Like maybe there was more being seen than being shared. Why did professional images show only a blur when amateurs seemed to catch structure and shape? Why were the published papers deep diving into technical stuff, carbon dioxide ratios, dust polarization, but not even mentioning the obvious visual differences that anyone could spot? Was this just about different image processing tricks, or the kinds of questions pros and amateurs ask? Or was there a deeper reluctance to admit that something didn't fit the comet story, that maybe the models we trusted weren't as complete as we like to think? It's both, really. A mix of real scientific caution and plain old institutional inertia that slows down big changes. Science leans conservative on purpose, shaped by years of embarrassing missteps whenever people jumped too quickly onto wild new ideas that later fell apart. The whole system prefers the tried and true, only changing its mind when the evidence stacks up so high you just can't ignore it anymore. This way, researchers don't get swept up by excitement or random patterns that don't mean anything. But this careful approach also breeds a kind of stubbornness. People get attached to old categories, comfortable explanations. So when something truly new comes along, something that doesn't fit, the instinct is to stretch the old framework as far as possible. Maybe add a few tweaks or extra parameters, but rarely do they tear everything down and start fresh. That's why 3IATLAS is still officially called a comet. It's in the databases as one, the papers talk about it as one, even though the more you dig into the details, the less that label fits. Look at the timeline. It showed up in July, spotted entering the inner solar system from interstellar space. By late October, it swung closest to the sun, prime time for observations. This was when it should have been brightest, easiest to study in detail. November, amateur astronomers caught images that didn't match what the pros had been showing. Then December rolled around and the object was heading away, fatting fast. Each day it got harder to study. There just wasn't enough light for clear spectroscopy or sharp images. Longer exposures meant more trouble from tracking and the atmosphere. The chance to get really good data was slipping away fast. If you cared about 3IATLAS, you could feel the clock ticking. Space missions take years to plan and launch. By the time anyone could even start thinking about sending a probe, 3IATLAS would be billions of miles out, speeding away at tens of kilometers per second, way out of reach. Earth-based telescopes have hard limits. The farther the object, the fewer photons reach you, and the harder it is to see anything clearly. Unless this thing did something totally undeniable, pulled off a maneuver that broke physics, or beamed out a signal nobody could explain, it would just fade into the background. Too faint for good data, too dim to study, destined to become just another oddity in the records. Not explained, just quietly set aside. And that gets at the heart of the problem. The way we look for and study new things is built around what we expect to find. Our discovery tools, telescopes, detection software, classification systems, they're all tuned for objects that behave like the ones we already know. Telescopes track motion because that's how you spot planets and comets against the stars. Software flags weird stuff because it's programmed to notice things that break the pattern. But what if something new comes in and deliberately imitates what we expect? What if it wears a disguise, hiding under just enough comet-like activity to slip through unnoticed, blending into the noise? It's a real challenge, one that 3IATLAS throws right in our faces. Our detection systems just aren't built for this kind of thing. Nobody expected to need them. Until recently, the idea of an artificial object sneaking through our solar system belonged in sci-fi novels, not scientific papers. The tools we have are good at spotting rocks, ice, comets, anything natural that might threaten Earth. They track orbits, calculate impact odds, and keep an eye out for the usual suspects. But they're not set up to catch something pretending to be natural. Because, let's be honest, the whole field of solar system astronomy runs on the basic assumption that everything out here is natural. Gravity, collisions, slow-building chaos, that's what shapes the stuff we see. It's always been a safe bet up until now. 3IATLAS could still be a comet, just one with a handful of odd traits. Most of the evidence and most experts point that way. The object fits into the categories we know. But this discovery hasn't followed the usual script. There's no neat label, no comfortable match with existing models, no feeling of, oh, we've seen this before. The data just doesn't want to play along. It keeps slipping out of the patterns we expect. And in that mismatch, no matter how unlikely or unsettling, there's a crack of possibility. Maybe we're looking at something we haven't seen before. Maybe we'll need to rethink what's out there and how it gets here. Maybe our confidence about the universe is a little premature, built on too few examples and not enough real experience with what's actually moving around beyond our corner of space. At first, everything looked normal. Spectroscopy picked up water vapor, carbon dioxide, carbon monoxide, the usual chemical fingerprints of a comet waking up near the sun. Images showed a classic coma, that smudgy halo of gas and dust. A faint tail appeared as 3IATLAS swung in toward its closest approach. On paper, this was a comet, no question. Sure, it had crossed from interstellar space, but it didn't act much different from the comets born here. The first wave of scientific papers said as much, an interstellar comet, rich in carbon dioxide, showing all the normal signs of heating up under the sun. Then October 30, 2025 rolled around. 3IATLAS hit perihelion, about 1.4 astronomical units from the Sun, tucked just inside Mars's orbit. This is when comets usually go into overdrive, brighter, more active, shedding gas and dust as the Sun bakes them. Observers watched the brightness spike and the coma swell. But then things started to get weird. High-res images from big ground telescopes, the kind with adaptive optics, zoomed in on the nucleus. It looked more compact than the size estimates. The coma was there, but it wasn't as messy, less debris than you'd expect for something losing material at that rate. And the way the dust and ice scattered light, the polarization, just didn't line up with what's normal for comets. None of these things by themselves are a smoking gun. Science is messy. There are always outliers, oddballs, things that push the usual boundaries while still playing by the rules of physics. But when you start stacking up anomalies, when different measurements all hint that something's off, the question changes. It's not just, is this normal, anymore. It's, why is this object not acting the way we expect? It's a subtle shift, but it matters. It's the moment you stop trying to squeeze something into an old box and start wondering if you need a new box altogether. Astronomers, especially the teams at NASA's Jet Propulsion Lab and ESA's Near-Earth Object Coordination Center, didn't jump to conclusions. They kept calling 3IATLAS a comet in press releases. They told the public that interstellar objects are bound to be a little different. They come from other stellar neighborhoods after all. That's not spin. That's just how science works. You don't panic people with early findings that might not hold up. You wait for confirmation, for peer review, for other teams to see what you see. You share the most likely story, and you admit where you're not sure yet. But people can read caution the wrong way. For anyone following the story through independent channels or amateur astronomers, the official updates started to sound cagey, even evasive. Why did the professional images always show this fuzzy blob, while backyard telescopes caught real structure? Why did the published papers obsess over minor composition details but skate past those eye-catching visual oddities? Was it just different methods and image processing? Were people asking the wrong questions? Or was there some deeper reluctance to admit when the observations didn't fit the comet label? Honestly, it's a bit of both. Science leans conservative on purpose. It hangs on to what's already proven until the evidence leaves no room for doubt. That approach keeps us from jumping to wild conclusions on flimsy data, but it also slows things down. When something truly new shows up, something that doesn't fit the usual boxes, people instinctively try to squeeze it into the old boxes anyway. So 3IATLAS stays officially labeled as a comet, even as the evidence keeps piling up and making everyone squirm. Look at the timeline. They spotted it in July. It swung closest to the sun in late October. Amateurs started seeing structure in November. By December, it was already heading out, getting dimmer as it drifted away from both the sun and Earth. The best window for observations, gone in a flash. If 3IATLAS really is something unprecedented, we barely had a chance to study it. Space missions need years to plan. Ground telescopes can only do so much. Unless this thing does something flat-out impossible, like changing course in a way physics can't explain, or sending out a signal that can't be natural, it'll just fade into the background, another oddball in the catalog of cosmic mysteries. Here's the bigger problem. Our whole discovery process is built on certain expectations. Telescopes scan for motion because that's how we spot things moving against a sea of stars. Software flags what looks weird, but only based on what we already know. Now imagine something slips into the solar system that's deliberately acting natural. What if those comet-like flares are just a disguise hiding something more structured underneath? Our tools won't catch that. They're built to find rocks, ice, orbits, possible threats. They're not made to spot artificial objects pretending to be comets. Honestly, nobody took that idea seriously until recently. Maybe 3IATLAS really is a comet. Most of the data still points that way. But this time, the process didn't work like it was supposed to. The data doesn't fit neatly anywhere, no matter how hard people try. And in that stubborn refusal to cooperate, there's a chance, however slim, that we're looking at something outside our usual playbook. Something that might just force us to rethink what moves through space and why. Part 3. When the data stopped cooperating. The first real hint that something weird was going on. Something that didn't just make classification tricky, but flat-out clashed with what everyone expected. Didn't come from NASA or some famous observatory with a mountain of funding. Instead, it landed in the lap of Sarah Chen, a doctoral student at MIT. She's quiet, methodical, the type who gets lost in her data. At the time, she was knee-deep in her thesis on how interstellar dust plays with light. While digging through old polarimetric data from 3IATLAS, data taken before it even got close to the sun, back when it was just a faint speck, Chen stumbled onto something no one had really looked at yet. The data had just been sitting there, collected as part of a big survey, waiting for someone with enough patience to comb through it. Now, polarimetry isn't the first tool most astronomers reach for. Instead of just snapping pictures or breaking light into a rainbow with spectroscopy, polarimetry checks how light gets polarized, how its waves line up, after bouncing off surfaces or weaving through dust floating in space. Different surfaces and materials twist and turn the light in their own unique ways. By sifting through those patterns, researchers can piece together what an object is made of, how rough or smooth it is, and even how big or oddly shaped its dust grains are. It's a staple for anyone studying asteroids, moons, or the fuzzy comas around comets, since it gives away secrets about whether the dust is fresh or cooked, fluffy or dense, silicate or organic. So Chen starts analyzing the 3IATLAS data, and almost immediately she finds something that just doesn't belong. Her first thought, she must have messed up. Maybe a calibration step was off or the telescope glitched, but the numbers held up. 3IATLAS showed a negative polarization branch, deeper and narrower than anything ever seen in a comet or asteroid, even stranger than the wildest lab samples scientists have cooked up to test their theories. For those who speak the language, the polarization hit about negative 2.7% at small phase angles, with the inversion point, where it flips from negative to positive, hanging around 17 degrees. To most people, those numbers are just gobbledygook, but in her field they set off alarm bells. What does all that actually mean? In plain English, the dust and surface of 3IATLAS scatter sunlight in a way that doesn't fit anything we know. Not solar system comets, not interstellar dust between the stars, not any of the thousands of polarimetric records built up over 50 years. The particles are either way smaller than anyone expected, tiny nano-sized grains that shouldn't survive the brutal conditions of interstellar travel, or they're shaped in bizarre, unnatural ways. Maybe they're built from materials that simply don't exist in the catalog of known cosmic stuff, which would mean they formed through processes or under conditions we've never seen before. Whatever the answer, it's not in any textbook. Maybe the surface itself, the line where the solid nucleus meets the coma, has something weird going on. Texture, structure, layers in the material, who knows? Whatever it is, it messes with how light bounces off in ways you just don't see in comets around here. Chen's gut reaction: double-check everything. She started by questioning her own work, not the universe. That's just what good scientists do. You don't want to make a fuss and then have to walk it all back later. So she ran the data again, tried out different algorithms, played with all sorts of assumptions about how the instruments responded, tweaked the way she corrected for the atmosphere. She lined up her results with data from comets everyone already knows inside out, just to make sure her pipeline wasn't the problem. But the weirdness stuck around. The negative polarization branch for 3IATLAS was still deeper and narrower than anything anyone had ever seen. Didn't matter how she processed it, didn't matter what angle she took. It just wouldn't budge. She brought her advisor in, someone who'd seen just about everything in planetary science. He told her to send the data out, get other teams involved. Maybe it was something odd about MIT's instruments or their software, so Chen did exactly that. She handed the raw polarimetric data to groups at universities all over the US and Europe. Each team ran the numbers their own way, different software, different calibration tricks, their own assumptions. They all came back with the same answer. The polarization signal was real, not some glitch. Statistically, it stood out, way outside normal comet ranges. No artifact, no error. The data was telling them something about the surface or dust that just didn't fit the models. Chen put together a paper for the Astrophysical Journal, the top spot for this kind of research. She and her advisor made sure to stay cautious. No wild claims, just the facts. Sure, it was a big finding, but it didn't prove anything wild about where 3IATLAS came from, at least not yet. The peer review process would take months. Experts would pick apart the methods, dig into the conclusions. But the evidence was strong enough that people started talking about it in specialist forums and email lists, trading early takes before anything went on the official record. What happened next? Pretty much a case study in how science works when the data pokes holes in what everyone expects but doesn't quite blow things open. Observations push the limits but don't smash them. For months or even years, research just lives in that in-between space, not quite settled, not quite a revolution. Chen's paper circulated in the community before it ever appeared in print, showing up in inboxes and preprint servers. Some researchers got excited. They pointed out that this polarimetric oddity was just one of a bunch of little things about 3IATLAS that didn't add up. Sure, you could explain each weird detail if you stretched your models a bit. Maybe it's rich in carbon dioxide because it formed far from its star. Or the odd polarization was cosmic rays doing their thing for millions of years. Or maybe the thermal data was funky because of an odd shape or spin. But after a while, all those one-off explanations start to feel less like real understanding and more like a series of excuses, a way to defend the comet hypothesis instead of just following wherever the evidence leads. Some people weren't ready to jump on board with Chen's discovery. They pointed out that interstellar dust spends millions, even billions, of years out in the galaxy, getting bombarded by cosmic radiation. That kind of extreme exposure could easily give the dust weird optical properties we just don't see in the more sheltered dust floating around our own solar system. And really, the only other time we've tried to measure interstellar dust, those polarimetric studies of dust in molecular clouds, we might have only been seeing one flavor of it in one environment. Maybe 3IATLAS is something else entirely, with its own history, shaped by a totally different process. It could just be a reminder that our sample size is tiny, and every new piece of evidence shakes up what we think we know. But Chen's result wasn't the only thing acting strange. Around the same time, the team at Keck Observatory in Hawaii picked up something odd in their spectroscopic data. They saw molecular emissions from 3IATLAS that weren't smeared out across the whole coma. Instead, the molecules were hanging out in specific regions, not scattered at random. That's not how comets usually behave. Normally, as a comet spins and sunlight hits new patches of ice, you get gas jets popping off in all directions. The whole thing is supposed to be messy and unpredictable, with the emission pattern shifting as the comet rotates. But the Keck data showed stable hotspots, regions that kept pumping out molecules, night after night. The pattern barely changed, even though the usual suspects like rotation and sunlight should have mixed things up. Dr. Michael Tors, who led the Keck observations, noted all of this in his technical report. He didn't call it out as especially weird, though. When a science journalist pressed him about it, he said, "Comets are complex objects. Variations in surface composition, subsurface structure, and thermal inertia can all produce unexpected emission patterns. We need more data before drawing conclusions about what this means for 3IATLAS. That's classic scientific caution. Acknowledge the oddness, don't get ahead of the evidence. Still, it leaves the real question hanging. If rotation and sunlight aren't driving this pattern, what is?" Then the amateur astronomers weighed in. People all over the world, some with backyard telescopes, others with serious gear, started reporting that 3IATLAS's tail just wouldn't behave. Normally, a comet's tail is pretty straightforward. The sun and solar wind shove dust and gas away from the nucleus, making a plume that points away from the sun. Sure, the shape and brightness can shift a bit depending on what's in the tail, but overall, it's supposed to be steady. Not this time. Observers saw the tail turn on and off, flicker, even disappear and then come back, with no obvious link to how far the comet was from the sun or how bright the sunlight was. One engineer in Colorado, David Ruiz, really dug in. Over 2 weeks in late November, whenever the weather let him, he snapped photos of 3IATLAS at roughly the same time each night. Some nights, the tail popped, bright and crisp. Other nights, it was barely there, only to flare up again later. Ruiz posted his images on Comet forums, asking if anyone else was seeing the same thing. Turns out they were. Observers from the US to Europe to Australia all reported similar weirdness. Some blamed it on the atmosphere or quirks in their cameras. Others wondered if the comet spun so slowly that active regions were hidden and revealed over time. But the changes seemed too quick for slow rotation and too organized to blame on the weather. Something about 3IATLAS just didn't add up. NASA didn't change its official position. Comets are unpredictable, they said. Outbursts happen. Jets turn on and off as fresh patches of ice get exposed and then run out. That's all true. We've seen it before and it's in the books. But what people were seeing with 3IATLAS went beyond the usual comet weirdness. It wasn't breaking the laws of physics, but you needed a very specific mix of factors, just the right interior structure, the right spin, to explain what was showing up in the data. And honestly, those explanations started to feel forced, like tacking on epicycles to keep a theory alive when the observations keep poking holes in it. Then came the thermal data, which just made things messier. Infrared readings, measuring the heat coming off the comet, hinted that 3IATLAS was either smaller and hotter than expected, or bigger and colder. Nobody could separate the actual nucleus from the surrounding coma in those wavelengths, so teams ran with different assumptions about the surface temperature and how efficiently it radiated heat. They ended up with different answers. This kind of ambiguity isn't rare in planetary science. Size and temperature often blend together in the data, so you get a range of possible combinations that fit what you see. But with 3IATLAS, the range was way wider than usual, and it left some big questions hanging. If the core is tiny, why is it pumping out so much activity? If it's big, why does it look so compact in detailed images? Trajectory worked through another curveball. As more observations rolled in, astronomers kept updating the orbit, pinning it down tighter and tighter. Its path was clearly hyperbolic. No doubt it came from interstellar space, but the exact track depended on little pushes from gas jets blasting off the surface. For most comets, these tiny nudges are easy to factor in. You measure how much gas is coming off, figure out the momentum, and adjust the orbit. With 3IATLAS, though, the numbers didn't add up. The acceleration needed to fit the orbit was either too big for the activity people actually saw, or it pointed in weird directions that didn't match what standard jet models predicted. Dr. Elena Martinez at JPL was right in the middle of this, working on the trajectory. At a conference in December, she said, "The orbital fit gets a lot better when we add a small sideways acceleration, but it's still a bit higher than we'd expect from the outgassing we've measured. That might mean we're missing some lopsided jet activity, or maybe there's another source of momentum we haven't caught." When scientists say, "another source," that's code for, we don't really know what's going on. It's a way of admitting the data doesn't line up neatly, that the models need tweaking, that something about 3IATLAS isn't playing by the usual comet rules. By early December, teams looking at different parts of 3IATLAS, polarization, spectra, images, orbits, were all running into strange results. None of these oddities by themselves proved anything wild. You could explain each one if you really tried by stretching the normal rules for comets, but taken together, they started to stack up. Polarization that didn't match any known comet, emission sources staying in place when they should wander, a tail that flickered in ways nobody expected, thermal data that refused to settle, accelerations that only made sense if you guessed at hidden jets. Add in the amateur astronomers' pictures showing structure, and suddenly the pattern's hard to brush off. Science isn't about taking a vote. The truth doesn't care how many people find a model awkward or how many weird results pile up. What really matters is hard evidence, stuff you can repeat, proof that stands up to scrutiny. Still, science can't just stick to comfortable old ideas when the facts keep poking holes in them. Eventually, you hit a breaking point and something's got to give. Right now, researchers looking at 3IATLAS are stuck at that crossroads. Has the old comet model outlived its use, or can it still handle what's turning up? Or is it time to rethink things from the ground up? No one's rushing to answer. The risk is huge. Call it wrong and say this interstellar object isn't a comet, then find out you blew it and your reputation takes a hit. So people hold off. They collect more data. They double-check everything. All the while, the object drifts farther away, gets dimmer, and the chance to figure it out slips through their fingers. Part 4. The architecture of uncertainty. There's a certain kind of silence in science, but it isn't about not knowing enough. It's about having too many half-answers. You see it late at night, in conference rooms where researchers trade notes and stare at data that ought to make sense but just won't line up. It creeps in after a talk, when someone finally asks the question everyone's been avoiding. It's there in the cautious wording of papers that describe strange results but stop short of calling them important. Right now, that's exactly where 3IATLAS sits, caught in this limbo, balanced between what the numbers show and what anyone's brave enough to claim. So mid-December 2025, NASA's Planetary Defense Coordination Office gathered about 30 scientists at the University of Maryland. They called it Interstellar Object Characterization, Lessons from 3IATLAS. The list included spectroscopists, dynamicists, planetary scientists, astrobiologists, the usual suspects. Officially, everyone was supposed to talk shop, how to tweak observation protocols, build better models for the next weird rock that flies in from another star. But really, everyone was there because nobody knew quite what to make of an object that just wouldn't behave according to plan. No journalists were allowed in. No live stream, no public summary. That's pretty normal. These sessions are where people float wild ideas and shoot them down, without worrying about headlines or Twitter threads. Of course, it also means the real conversations are murky, pieced together from off-record chats and the sanitized meeting notes that eventually trickle out. Still, people who talked to reporters later said the mood was friendly but tense. Everyone agreed. 3IATLAS was weird. Nobody agreed what weird actually meant. One group, mostly from big-name planetary science programs at places like Arizona and Caltech, tried to fit things into known boxes. They said maybe it's a rubble pile with empty gaps inside, messing with its heat signature. Maybe its surface is loaded with CO2 but missing water, which would mean it formed somewhere cold, far from its original star. And after millions of years in deep space, cosmic rays could have zapped the dust, explaining the odd polarization. No new physics needed, just a comet with a stranger backstory than most. But another group, fewer people but louder, pushed back. Sure, each anomaly had a possible explanation, but you had to stack up a whole string of maybes to make it work, and the pile was starting to look shaky. Maybe cosmic rays changed the dust, but did that really produce the exact polarization they saw? Maybe empty spaces inside the object threw off the thermal readings, but did that explain why size estimates jumped around so much? Maybe jets of gas pushed it off course, but then why did its emissions look so steady? One fix after another, they said, just patched holes without building a real case. The data quietly refused to cooperate. Nobody settled the argument, they couldn't. The data just isn't there. 3IATLAS is millions of kilometers away, a tiny, stubborn dot drifting through space, only visible through telescopes that can't do miracles. We can't land on it. We can't send a probe close enough to snap a clear picture. All we get is light, photons bouncing off or coming from the object, filtered by space and our own atmosphere. Making sense of that light means building models, and when those models fall short, we're stuck. Interpretation turns into a kind of negotiation. How much weirdness are you willing to accept before you decide the whole framework needs to change? In the end, everyone's left in that uncomfortable silence, waiting for the universe to give up a little more. Dr. Avi Loeb showed up at the workshop. No surprise there. He's the Harvard astronomer who shot to fame after suggesting that 1/Oumuamua might actually be artificial. True to form, Loeb pushed for a serious look at non-natural explanations this time, too. Everyone knows his stance by now. Scientists shouldn't just shrug off the idea of alien technology when strange objects show up. With 3IATLAS, he pointed out how its odd structure, spotted by amateur telescopes, and its weird physical traits documented by the pros, at least deserve a real investigation. Not that he's declaring it's artificial. He just wants the idea on the table to be tested against the facts. People in the room took it in different ways. Some respected Loeb for saying what others only whispered. Others rolled their eyes, worrying that jumping to the alien angle too soon gives fuel to wild speculation and chips away at science's ability to draw the line between real evidence and wishful thinking. This kind of back and forth isn't new. It pops up anytime weird data lands in a field where the stakes are huge. Deep down, it's really about how science should handle its own edge cases. Should we play it safe and wait for bulletproof evidence before talking about extraordinary claims? Or should we keep all the doors open, even when it means poking at ideas that make people uncomfortable? Honestly, science does both, and it's almost never tidy. Some researchers lean cautious, others more daring. It depends on personality, career worries, how much controversy they can stomach. Institutions usually opt for caution, since their whole reputation is on the line. But breakthroughs often need someone willing to cross the line, ask the hard stuff, and risk looking foolish just to get us a little closer to the truth. With 3IATLAS, the community is stuck right in the middle, trying not to brush off oddities too quickly, but also not wanting to get carried away by them. Meanwhile, outside the neat little bubble of academia, the 3IATLAS conversation was taking off in a whole different way. Space enthusiasts, SETI fans, and people who just love a good mystery pounced on the amateur images and the holes in the official story. Theories exploded online. Some folks decided 3IATLAS was a probe, sent by aliens to snoop around the solar system. Others said it was an old, broken spacecraft, drifting after some ancient mission went off the rails. A few imagined a natural object, but one that got tweaked, maybe mined, maybe built on, by machines during its trip through interstellar space. The ideas ranged from clever to flat-out wild, grounded in real physics to totally off the map. But they all shared a gut feeling. The comet explanation just didn't cut it. Something about the official word felt thin, or maybe even like a cover-up. This is what uncertainty looks like up close, when nobody has a clear answer. Speculation floods in to fill the gap. If scientists say, "We don't know yet," some people hear, "We know, but we're hiding it." If the data's murky, some folks take that as proof of a cover-up, not just a reminder of science's limits. So you end up with two tracks: careful, cautious science on one side and restless, creative public chatter on the other. In between those tracks, things get murky. Nuance gets lost. Real science, with all its messiness and doubt, collides with tidy stories people want to believe. That's where the truth can slip through the cracks. What makes this tough is that the speculation isn't just hot air. The amateur photos really do show structure. The polarization signal, that's real too. And the way this thing moves through space doesn't add up perfectly. These aren't just rumors, they're facts, recorded and out there for anyone to check. The real puzzle is what to make of it all. That's where experience and judgment come in. Scientists who have spent decades studying comets bring a kind of background that you just won't find in an online thread. They know how often weird data turns out to be a glitch, a misread, or just something rare but totally natural. They remember all the past scares, objects that looked bizarre until better data made them boring again. That kind of context makes people cautious. They don't jump to wild conclusions. They want to rule out every ordinary answer first. But context can also close your eyes. Spend your life assuming every little thing drifting through space is natural, and before you know it, that idea colors everything you see. Anomalies get explained away, not always because the explanation is convincing, but because the alternative, that something might actually be unnatural, just feels too wild to face. It's not some conspiracy. It's just how people think when they're weighed down by everything they already know. We see what we expect. When something doesn't fit, we bend over backwards to make it fit, long before we're ready to admit we might be wrong. That's the real balancing act for anyone following 3IATLAS right now. You have to respect the cautious approach that keeps us from leaping to conclusions, but you also need to stay open to the idea that this object might actually be something new. The data isn't complete, sure, but even incomplete data can tell you something important. Most oddities end up with ordinary explanations, but sometimes, just once in a while, the anomaly is real and we have to rewrite what we thought we knew. It's not easy to walk that line. It takes humility, patience, and a willingness to sit with not knowing. Meanwhile, time running out. As December 2025 ticks by, 3IATLAS is heading out, getting harder to see. Soon, only the biggest telescopes will even have a shot at following it. By spring, it might be too faint to study in any detail. What we've got now is probably most of what we'll ever get. unless it suddenly does something wild and grabs everyone's attention. So yeah, the uncertainty we're dealing with now might just stick with us, unless another interstellar visitor swings by and gives us a better frame of reference for what we're seeing. Part 5, the open question. Science doesn't really give us tidy endings. Mysteries don't wrap up with all the answers laid out, every loose thread neatly tied. They shift, they grow clearer, but they rarely disappear. We move from we have no idea to well, we know more than before, but we're still in the dark about some things. Sometimes questions just hang there, unresolved, waiting for better data or sharper theories. That's where 3IATLAS sits now. Nobody's cracked it and nobody's tossed it aside. It's just there, an open question among the other odd visitors to our solar system, carrying secrets we can't quite unlock yet. People have seen this odd structure in amateur images, and those sightings haven't been debunked. Different observers, different times, same result. Folks have tried to recreate the images with similar gear and methods, and they've pulled it off. So the structure's real in the sense that it keeps showing up under certain conditions. The tricky part is figuring out what it means. Is it something in the nucleus itself? Or is it just a trick of the light, the way the coma looks from our angle? That's still up in the air. When the pros point their fancy telescopes at 3IATLAS, they see something fuzzier, less defined. The two views just don't line up, and with time running out to observe, maybe they never will. Then there's the polarimetric oddity. Sarah Chen wrote a paper about it, and after a good hard look, the journal accepted it. So now, the weird negative polarization branch of 3IATLAS is officially on the books. Researchers studying how cosmic rays mess with interstellar dust have added this as a possible case of extreme processing. But honestly, the explanation feels shaky. It depends on everything lining up just so. A dust mix and grain size we haven't actually seen. If those details are off, the theory falls apart. So, the mystery stays alive, and new ideas are more than welcome. The Keck team picked up some unusual, orderly emissions, less chaotic than what we see from regular comets. Papers have tried to explain it using models for outgassing. Maybe there's hidden structure beneath the surface, or some patches of ice that hold heat and release gas in bursts. All that could fit the facts. Still, these ideas came after the fact. They weren't predictions. When you're tweaking models to match the data instead of the other way around, you start to lose confidence. You end up describing what you see, not really understanding why it happens. The weird accelerations are still bugging the folks who chart orbits. With data through December, the latest models need to assume jets pushing the comet along, but nobody's actually seen those jets. Some think the comet spins slowly, maybe over several days, letting active areas soak up sunlight and push it off course. That's possible, uncommon for comets, but it happens. Still, there's no solid evidence for it. No repeating patterns in brightness or emissions, nothing concrete. Right now, it's just a guess to make the math work. In January 2026, Dr. Michael Tors and his team pulled together everything we know about 3IATLAS into one big paper. Physical characterization of interstellar comet 3IATLAS, composition, activity, and structural properties. It's a solid piece of work, thorough, careful, making sense of a comet that's strange, but not completely beyond explanation. They lay out the case. Maybe the comet's rich in carbon dioxide because it formed in a cold, distant disk. Maybe cosmic rays changed its surface during its long journey. Maybe its insides are a messy rubble pile, causing weird outgassing. The paper admits there are gaps and places where the models don't quite fit. They call for better observations with better tools. All in all, it's honest science, good work, but the story not finished. Still, the paper felt incomplete. If you read closely, you could sense the tension. What wasn't said mattered as much as what was. The authors worked hard to make 3IATLAS fit into the comet category, and they pulled it off well enough to satisfy peer review and most of their colleagues. But the fit wasn't easy. They had to pick and choose which data to highlight, which details to let fade into the background. They leaned on reasonable but unproven assumptions. Some questions just hung there, not because the scientists missed something, but because the data itself refused to settle into a tidy answer. So what would it have taken to reach a different conclusion? What kind of observation or evidence would have forced the authors to say, "This isn't a comet"? The answer's maddeningly unclear. A radio signal would do it, or a maneuver that broke Newton's laws. If they'd found industrial materials, refined metals, or spectral lines hinting at technology instead of geology, any of that would have shattered the natural explanation and forced a serious look at artificial origins. But without that kind of smoking gun evidence, the ambiguity lingers, and with it, the possibility remains. By February 2026, 3IATLAS had faded to magnitude 22, visible only through the biggest research telescopes, and even then only with long exposures. Astronomers moved on to closer, more urgent targets. The interstellar visitor slipped out of the spotlight, drifting outward on its hyperbolic path, heading for deep space. In a few years, it'll pass Neptune. In a few decades, it'll leave the sun's influence for good, joining the galaxy's vast crowd of wanderers. We won't see it again. The scientific community is already shifting its attention. Soon, we'll find other interstellar objects. The Vera C. Rubin Observatory is about to start full operations, and once it does, the pace of discoveries will jump. Over the next decade, we might spot dozens of these visitors, each one a new chance to refine our theories or test wild ideas. 3IATLAS will turn into a reference point, something to cite and compare, its oddities either explained as part of a larger pattern or written off as one-off weirdness. Time will put it in context, but time alone won't reveal what it really was. So we're left with the question, was 3IATLAS just an odd comet, shaped by cosmic forces we're only starting to grasp? Or was it something stranger, something that disguised itself well enough to slip through our solar system without tipping its hand, leaving before we could get the proof we needed to call it what it was? The data supports both stories. The first seems more likely. The second is harder to swallow, and honestly, we may never know. There's nothing satisfying about this ending. No neat resolution, no dramatic twist where everything clicks into place, but it's honest. Science often stops at this edge, where the facts run out and interpretation takes over. We can say what we saw. We can offer our best guess at what it means. But sometimes, we just can't say what a thing is. And that space, between what we observe and what's actually true, is where the most interesting questions live. 3IATLAS showed us that interstellar objects are more varied than we expected, that the universe between the stars shapes matter in ways we're only starting to notice. Our models are useful, but they're provisional, built from too few examples and tested on familiar ground. When something new shows up, those models get stretched. Sometimes they hold, sometimes they break. We don't know yet which side of that line 3IATLAS falls on. Maybe, when more of these objects turn up, we'll finally be able to tell if it was a lone oddball or the first sign of a bigger pattern. Until then, the answer stays just out of reach. We know one thing for sure. There's a whole lot up there we haven't seen yet. Space between the stars isn't empty. It's packed with debris from billions of planetary systems. Stuff that got tossed out long ago, drifting through the galaxy, sometimes passing close to stars like our own. Most of it's tiny, frozen, and invisible, unless it wanders near enough to a star to heat up and show itself. Only now are we building the tools we need, the telescopes, the algorithms, to catch these wayward objects before they vanish again. Every one we spot adds something new, another clue about what's really out there beyond our little patch of sky. 3IATLAS is one of those clues. It doesn't fit neatly. It's a weird piece, the kind that makes you uncomfortable because it doesn't go where you expect. But it's just one piece. More are coming. When they do, we'll be watching, measuring, asking questions. We'll line them up next to 3IATLAS, looking for patterns, trying to prove or disprove the wild ideas this object has kicked up. We'll get sharper at telling natural from artificial, weird from impossible. Or maybe we'll realize those lines are blurry, that the universe can make things that don't fit our categories, that sometimes geology starts to look a bit like technology and luck can mimic intention. 3IATLAS doesn't leave us with, was it artificial? That's not the real question. The real question is, how would we even know? What rules do we set? What counts as proof? And when the next, even stranger object shows up, will we see it for what it is? Or will we do what we did before, find ways to explain it away, bend our models, hang onto the idea that we're alone, that everything floating through the galaxy is just rock and ice, nothing more? There aren't answers yet. We carry those questions forward, into the next discovery, the next pile of data, the next late-night argument in a half-lit conference room when the numbers don't add up. These are the questions that keep science alive, that turn it from a list of facts into a real adventure, a way of learning to see what's been hiding in plain sight, of asking things we didn't even know we should ask. 3IATLAS is gone now, fading into the dark. But the strange features it showed us, the things that didn't add up, the questions it left behind, those stick around. They live on in the data, the research papers, the conversations in labs and online, in the minds of everyone who looks up and wonders what else is out there. They're still with us because we never really answered them. We just set them aside, waiting for more evidence, for better tools, for the nerve to face them head-on. Maybe that's the real lesson here. Not whether 3IATLAS was artificial or not, but that the universe doesn't owe us comfort. Sometimes the data fights back. Sometimes what we see refuses to fit the boxes we've made. And when that happens, the honest thing, the only thing, is to admit we don't know, to keep the question open and keep searching. Because the next object is already on its way, somewhere out there between the stars, heading for us along a path we can't see yet. When it gets here, we'll be ready. Or at least we'll do our best. The sky's full of questions. 3IATLAS is one of them. That question's still waiting for an answer.